I hope. Okay, let's start. So we have discussed basics of neural network. So right now we'll discuss overall architecture and some basic equations. Okay, so we'll come to this architecture. This is the overall architecture, and you can see the inputs are P1, P2, P3 parameters or features, and it is going to the neural network and weights the other W11, W12 is goes on a lot of weights, and WSR is the general last weight, and there is a summation. There is a summation with bias b1 is added to each of this summing units, and then it goes to activation function, and after activation function you're getting the output of the that layer. Okay, so these things we have discussed. Now how we calculate it using a metric notation, that will be, so all these things are very easy for a computational point of view or for a software or something. So we need to convert into a simplified way. So this is the general thing. Input r as parameters, r into one vector, go into w vector. W is a matrix, so we'll just represent each of this weight matrix as total, a big matrix w. All the input is r matrix, parameter matrix. There are r in number, column matrix, or that depends. That depends upon the how many. How many number of inputs you need to give and all those things. P is the parameters and B is the biases, and then it is summing unit, then activation function, the output is getting. Okay, so let's just overall see how this is working. Okay, so this we'll just see what are the important equations and all those things, passing information. So we know there are different inputs. We have different inputs like P1, P2, Pn, lot of, and if n inputs are the pieces of the input, and this will be multiplied by the weights. Like this P1 is multiplied by W1, P2 should be multiplied by W2, and so on and so forth. And Pn should be multiplied by Wn, right? And these all will be going to next layer or output, whatever according to this. So this is going to be Y1 layer, right? So Y1 maybe you can say activation function. If there is a bias, also bias B. Okay, so assume there is no bias. So in simplified case, we can assume there is no bias. So even if there is no bias, ideally you can put bias 0 or something, or we can not may not take bias for the right now. So we can see the equations of y1. You can see the y1 equation will be coming about what? Here coming activation. We are going for activation of what? Input to y1, signals input to y1, that is w1 into x1 plus w2 into x2 plus w3 into x3. This is the input to the activation function, right? So the output of the neuron is the activation function of a weighted sum of the neuron input. So all the weighted sum is going to the weighted sum of the input is going to this node, and the output is the activation function of this weighted sum. Right. Now this is the case of only one neuron. Now we can say that I'm using only one neuron. So these are different dendrites, different dendrons, and this is the dendrites. This is the dendrites of different neurons, and these dendrites are catching this signal and giving to the neuron body, cell body, and the output is the activation function output. Okay. Now let's see if there are two neurons. What will happen if there are two neurons? So okay, so we have three inputs. We have taken three inputs. So here also we'll take three inputs. X1, or let's say P. Okay, let's take P. Okay, so this is say P1, P2, P3. Let's take P1, P2, P3. Okay, and we have right now we have two neurons. This is Y1 and this is Y2. Two neurons as well. Okay, let's connect this. Now from P1 parameter 1 is input is going to Y1, and the input is going to Y2, right? So this is going to neuron 1, as the input is going to neuron 1, I'll call this W weight of going to neuron 1 from the first parameter. Right. Now second is W2, neuron 2, the weight which is on the weight to the neuron 2 from the first parameter, first input, like that. Okay. Now what about the other inputs? I will be naming like this: x2. From the x2, I'll be passing to the y1 and also to the y1 and y2. So here I'll name input to here also w1, this first neuron from the parameter 2, w1 2, right? And what about this input to the second neuron from the parameter 2, right? Again, terminology is important because we want to write the notation, matrix notation kind of thing. So here the input is going to the two neuron from the second parameter also. So this is first neuron is going to input is going to first neuron from the third input node. So this is also going to the second neuron from the third node. Okay. So I think you got the terminology what we are trying to hear. Okay. So in this example, the first layer is connected to each neuron of the second layer. Right. Each neuron of the second layer. Okay. So it's called fully connected network. You can see from each parameter, I'm going input to both of these neurons. So it's fully connected network. So how can you write the equation of y1 here? Here equation of y1 you can write y1 equal to same things w11 into p1 plus w12 into p2. You can see the second node, and one more thing is coming from p3, that is w13 into p3. Okay. Now what about y2? Y2 same thing. First is y2 w21 into p1 plus w22 into p2 plus w23 into p3. Okay. So you can see if there are two neurons, this is your outputs. Now this you can see this is kind of metric multiplication. If you see closely, you can see this is kind of metric multiplication. Can you see this? You can see w1 into p1 and then this w1 into, so this you can write how you can write this matrix multiplication. Can you write like this: w11 w12 w13. This is multiplied with the column, right? p1 p2 p3. Can you write like this? You can see this is a matrix. If this is a matrix, if this is one matrix of row w11 and w12 w13, and if this is the input matrix, how will multiply? w11 into p1, right? This is multiplied like this now. w11 into p1, w12 into p2, right? So all these things we are done. All this doing using this metric multiplication. Now what about the second row? Second row also if I write like this, weight matrix w21 here into p1, yeah, done. w22 into p2, that is also done. w23 into p3, right? So this is kind of metric multiplication, you can see, right? So this multiplication gives you the answer in two rows. First row you'll get y1, output is y1, first row this is y1, and second is y2. So this is your output of this metric. You can see this is clear. Very simple. We are using metric notation for simplification. Now we need to write a weight matrix. According to weight matrix, we have to write the weights connected to neuron 1 is w1, 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 w12, w13. A weight connected to neuron 2 is w21, w22, w23. Okay, and this multiplied with the input matrix or transpose of the input. We can write anything. So this is the input matrix. All the parameters are in this matrix. Okay, and this is multiplied and we get the output y1 and y2. Okay, so general how can write general equation? The general equation we can write like this: output. This is the, you can say output nth output equal to weights WIGHTH, weights of n minus 1, right? Because these weights are leading to the current output. This is previous weights, leading to the current output. Why I'm saying previous weights? Because each iteration I have to modify the weight. That is the training, right? So I cannot make the weights always constant. I have to modify it. So I have to write like this: n minus one weight. This is n minus one weights is helping me to get the nth output into input, input, input. So based on this equation, I should write like output nth output equal to n minus one weights into inputs. So input you should know this is the parameters p1, p2, p3. These are parameters multiplied by the weights give me the output. So your n minus one weights multiplied by the input will gives the nth output. Okay. Now if we have multiple weights, right now we have I think we are not used activation function. Now let's see if we use activation function, the output has to go to the activation function, right? So if we are using activation function, it should show here that there should be an activation function also. So y1 should be going to an activation function, or you can see a for a whatever. So y2 should also be going to an activation function. Now you get another output, here. So how to represent that? So then you have to write like this. So now the output, this output again has to go to activation function. So nth output equal to activation function, activation of weights, and n minus one's weights into output n minus 1. Okay, so all these things are going to the activation function. So I have to write like this. Now whatever output we have got is going to the activation function like this. Output activation function. Okay, so just for generalizing this thing. Now let's say what about training? Now we can tell about the training. So training is, we need to compare the actual value. For example, we are inputting a parameters of a boy or a girl, right? So the network is the model. The neural network model is analyzing and giving that this is a boy. Input is a girl, but it is telling that it's a boy. So, but it is a training. This is in the training phase. We already know that okay, this is a girl. This should be a girl, but the neural network is telling it's a boy. That means error. So this error, this error. What is error? Your output, actual output minus expected output. Right, actual output should be girl. That we know. That is in training phase. We know the labels of each input, but we are getting output boy. So there's an error. So the error equal to actual output minus expected. So I'll just subtract this to actual minus expected. So this is going to subtracting unit. This is actual output we already know, and this is getting an error. Now, based on this error, what we need to do? We need to change the model. This is called changing the model. We need to train the model, right? So error is going to the model, and what will be changing? Weights in the model is going to be changed. W1, W2, W3, and all those things will be changed with delta W and delta will be added with the model weights, so that we are updating the weights, so that error is next time the error is not there. So this is ultimately the purpose of training. Now let's see how on what ratio, how we are going to modify the weights. That is the question. Error we have calculated, error function we have calculated. There are different types of error function, and based on this error function we need to calculate the error, subtract it from the actual, and now this error has to modify my weights. Now how we are going to modify the weights? That's the question. Okay, so in this case we can take an example. So there are two inputs, parameter 1, parameter 2 is going to the output y1. Okay, so here we are assuming the y layer is the output layer of the network, and y1 neuron should return some value. It should return some value. Now this value can be different from the expected value. There can be error. That is, we are expecting a girl, but we got the output boy. So there is an error. Okay, there can be some error. So there should be error on the y1 neuron. So we should take the difference of the actual and the expected value, and this error, we need to pass this error to the backward. Okay, so all these neurons, we should pass the error to the backward layers, so that all the neurons can learn, right? So the question is how to pass the error. And one thing is the error, whatever error in the output. One thing, there is some error. Okay, this error. So this error can be equally passed to both these neurons. This is change here, change here. This is W1, this is W2. I should equally pass this error to both of these neurons. Right, there are two neurons. Technically, we should write like this. We are discuss this instead of W1, W2. We were discussing this as is going to first neuron. So going to first neuron. So is going W1, 1, W1, 2, something like this. Okay. So the error has to be equally updating W11 and W12. But there is a problem here. Say if the W11 is having a higher weight, if the W11 is having a higher weight, much larger value than W12, that means this has given a higher error. This has resulted in a higher error because of this higher value of W12, W11. And W12, for example, the W12 initially may be 5, for example, W12 may be initially 0.3 or something. You can see this is W11 is helping improving the multiplying with the P1 and giving a greater part of the output is caused due to the W11, right? So as per the logic, we should remember that we have to change W11 more, reduce W11 more than W12 because it is negligible. It is only value is very less. So the error has to be distributed not equally, but as per the ratio of the weights, right? So one option is instead of here the case is W11 is much greater than W12, something like this. Here we should not distribute the error equally because reducing W12 doesn't have much logic reasoning because it's already small. So we should have more reduction in the W11. So we can say one option is based on the ratio of W1 and W12, we should reduce their value W11, W12. For example, error error because of P1, error of the P1 input, right? That is can be also error which has been changed the weights of the P1, EP1. The ratio of W11, W11 plus W12. This is one ratio which based on which I can change my W11. Ratio of the weight of the present neuron to the total sum of the neurons into error on Y1, what we are getting, EY1. This is getting EY1 here. EY1 error here. Okay. And similarly, what is the error P2? That is W12 divided by W11 plus W12 into error on Y1. Okay. So this is one logic. Now what if there are two output? What if there are two output? So there are P1, P2 connected to Y1, Y2. So P1 will be connected to both of these neurons, two neurons. This is two neurons. Okay, and same time P2 is also connected to first neuron, second neuron. Okay, so this weights we have decided this is W11, this is W12. What about this? This is W21, this is W22. Based on the neuron we are counting. Anyway, so there is an error EY1 here, there is an error EY2 here. Now, how I am going to propagate this error into my neurons weights? How I am going to reduce the weights? Now, this based on this error EY1, this error EY1 has to be utilized to change the weights of P1 parameter P1. This has to be utilized to change the weights of input parameter P1. So I call EP1. This should be the value EP1. Both W11 and W21 should be changed in the rate EP1, and based on the error EY2, I have to make some numerical calculation so that I can change the weights connected to parameter P2. That's I call EP2. Now there are two things. each P2 have two things, W12 and W22. Similarly, P1 has two weights, W11 and W21. So one option is I can write an equation like this: EP1 is equal to, there are two weights, so I should, there are two errors also. So the error 2 is also caused. You can see there is a link here. Error 2, EY2, there is some reason why P1 is also causing the error. P1, P2 is also causing the error. P1 and P2 both resulting in the EY2. Same time, E1 is also caused by the P1 input multiplied by weight 1, 2, as well as, sorry, P2 input multiplied by weights 1, 2, as well as P1 input multiplied by weights 1, 1. Okay, so this error has to be propagated back to the input. So one option is, based on its ratio, we have to increment the W. So just write, need more space. Okay. So one option is I can write like this: E P1, error P1, which has to be propagated to the weights, is ratio of the weights here also, W11 divided by W11 plus W12. Weights of the neuron, ratio of the weights connected to neuron 1 into the error EY1 error, plus again now you have to change to come to EP2. Yeah, based on the second neuron, to change. That is W21 W21 is, yeah, W21 is this, W21 divided by W21 plus what is the other weight, W22, right? W21 plus W22 into error EY2. Okay, so this error is modifying the P2, as well as EY1 is modifying the P1 weights. Okay, likewise we can write the equation for EP2 also. Error due to the P2 is equal to W12 plus W12. We can see this now. This EP2 is also caused, this error EY1 is also affecting because of this weights W12 also. So I have to write like this: W12 divided by W11 plus W12 into EY1 plus, now the second one EY2. EY2 is also causing, the error is also EY2. That is also caused by this W22 as well as W21. This two error. Okay, so I should write W22 divided by W21 plus W22 into EY2. Okay, so I'll give you the link. You don't need to write. I will give you the link for this notes from the web page. I'll give you this. So net result, I can write this equation what we have just written like this: EX error from the input P. So instead of P equal to W11 divided by W11 plus W12 W21. This is a similar equation which you write in the top. We can reduce into matrix multiplication. Okay, the logic you can understand. This is only one method of updating the weight. There are different methods, but this is, I'm just telling you logical. How much, based on the ratio of the weights, we can multiply this weight. W22 divided by W21 plus W22. So this weights ratio multiplied by error EY1, EY2. Okay, I think this sounds logical a bit. Okay, so the idea is, if we eliminate the common factor, we can see the normalization of the weights. If we eliminate this normalization thing, we can see here all both this are same, this and this are same. We can see this and this are same. So if you are able to eliminate, if you eliminate this guy, you can see this symmetrically. It's very simple. Now the equation becomes very simple. Yeah. If you ask me why it can be eliminated, yeah, this can be eliminated for the simplicity of the calculation. So I can this is W11, W21, W12, W22. Okay. This is nothing but EP. This multiplied by error function, error coming from the individual output. Okay, so we can see this, we can see in matrix form, we can see this should be first element 1 1, this should be 1 2, but here we have 2 1, but this should be 2 1, but we have 1 2, and this is fine, these two things are right. So we can see this is a transpose, this is nothing but a transpose of what, w11 w12 w21 w22, right? This is nothing but a transpose of this matrix, which we know as a weight matrix, which you already know weight matrix. So we can simplify this based on this thing. We can simplify this equation. We can write like this, that error n minus 1th error equal to w nth weight transpose multiplied by nth error. Okay, so this is you can say this is what we are coming is called back propagation algorithm. Back propagation algorithm. This is the most important. If you know this thing, at least I think you know one complete neural network thing. So that we are trying to modify. We are coming to the back propagation algorithm. So this weight transpose is again multiplied by the error, existing error. Okay, again multiplying the error. Okay, now this is update. This is update for the n minus 1 neuron, n minus 1's neurons. Okay, so this is the most basic equations for a simple neural network. So back propagation, what is back propagation? We are calculating error, and this error is propagated backside towards the neurons weights, so that we are updating weights according to the ratio of their neurons, something like this. So ideally this should be the expression, but we can reduce or simplify it so that it will help our purpose. Okay, so I'll share the link. We can go through it, some interesting link. So I think right now we are in a position to simulate a small neural network model. We'll take a small application like character recognition or something, and we'll feel it, how it is happening. So it'll be a good thing. Maybe we can use Python or MATLAB, whatever, but at least we should know what is the input, how is this training, and how the error is found, how the weights are updated, and how much training and how much testing and verification we have to give, so that we are getting perfect output. So I'll share you a small piece of code so that you will get a feel of this neural network. So that is important, especially when you're working on deep neural network or maybe some project related to artificial neural network. So ultimately, what is our agenda? And we can see this is the another weight update equation. We can see this is a differential, this is a gradient, this is a gradient here. Error with respect to weight. This is net weight, old weight, this update, this weight has to be updated. So this old weight minus a learning rate, A. What is learning rate? So based on the error change, we can, it's up to the designer or the engineer to tell how much I should update the weights. Say for example, I have weight 5 and another weight is 0.4. So should I update this to dramatically to 5 to 10, 0.4 to maybe 20 or something? That is not good actually. Update should be slow. So whatever constant we are multiplying our weights or adding our weight should be multiplied by learning factor. Learning factor is maybe values, maybe 0.1, maybe 0.2, or maybe 0.05, or very small. It can be very small, because whenever we are learning, we need to learn it step by step, so that the weights are updated slowly, so that we'll reach the optimum weights. Because there is always, you seen the objective function, this error is always the, you have to come slowly to the optimum weights, right? So this is our minimization. This is a minimization problem. We are trying to reduce the error to the minimum. So if we put the learning rate a very small rate, it is efficient. If we give a big error rate, So it will be jumping, although it may fast, it will be coming faster to the, but even it may not go to minimize. It will jump here and there. Again, it may go here, it may jump here, it may go here. Again, it may jump. So it may not helpful for. So if we go step by step very slowly, we are moving more stable operations. That means learning rate is there. We are going step by step by step by step by step. We will not miss the minimum. Will not miss the minimum. Else, we'll miss the minimum. Right. So this is a very important of learning rate. Learning rate. How much steps you have to take. So this is learning rate is already put in 0.1, 0.2, 0.5, so that we'll approach the minimum in a step-by-step fashion. We don't miss the minimum also. Else it is very challenging and depends upon the problem. Depends on the problem also. Sometimes there is another some algorithm says that initially you can give a higher learning rate. Maybe I can like step by step. Then I should go slowly, 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 slowly. Then I'll approach the minimum. So there are different algorithms in this. That way, a lot of research papers we can also think about something changing the learning rate dynamically. So ultimately, this is the error. Using the error, we are finding the error derivative. You can see you remember gradient descent. Gradient descent. What is it? Is finding the slope of the error function, and based on the slope, it is going to that direction where my error is minimum. So this is also gradient descent. Derivative of weight or error. Sorry, derivative of error with respect to the weights. Okay, and based on that direction, we are going slowly, 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 slowly to the minimum point where our error is minimum. Okay, so this is also weight update equation. The important thing is present weights plus or minus, usually minus, into a learning rate into derivative of weights or derivative of the error with respect to weights. Okay, so ultimately now we can appreciate this is a matrix. Every weight, this is also matrix. Weight equation is also matrix. And now this is a neuron output, first neuron output, second neuron output, third neuron output, like this. So A is also matrix. There are three here. There are many S number of layers, and each of the horizontal layers correspond to one neuron. So in the function is like this: W is a matrix, P is the matrix, B is another weight bias matrix. So this is simplified representation of a neuron network. Okay, so ultimately what we are trying to do now, we want to come the overall picture. What we are trying to do is we are trying to make a model. What is a model? In any engineering thing, we'll make a model of anything. It can be a automobile, it can be a factory, it can be a plant, it can be a machine, it can be a computer, whatever. Then what is what is the importance of model? Whatever input we can give to the real system. For example, we have real things, real world machine or real world system. So instead of this real world system, I can give some input, but some input it is not practical, and I have to predict what will the output if I give some input, some kind of prediction kind of thing. So in real world, I may not be able to give this input to the system because it may crash, system may crash, system may go burn, system may get destroyed. So a lot of problem happens in the real world. But in model, if I have mathematical model can be any type. Mathematical model can be this algebraic or geometrical, whatever. Then we have machine learning model, ML model, deep learning model. So there are different kinds of model, mathematically or anything. So what help it is going to model my real world system. So some input I'm giving here, I'm getting some output. So I should know in real world, if I give this, I'll get the similar output. So that means I can say this real system is, my model is perfect because my model is perfectly modeling the real system. So in engineering, we need a lot of modeling because before designing, before creation of application, we try to model it. Maybe mathematically, maybe block level using simulators or using machine learning or using other AI techniques, we can model it. There are a lot of mathematical techniques also, heuristic techniques, bio-inspired techniques, machine learning algorithms, right? Can model. So ultimately, we are trying to model a real world thing. It can be a factory, it can be a car, it can be a computer, it can be a digital system, analog, hydraulic, pneumatic, anything. So we are modeling, maybe using mathematics, machine learning, right? So the thing is, we can predict also what will happen after some time. After 100 years, will the model still works? So similar case will be there with the real world. Mostly, there will be not be fully applicable. Whatever model characteristics will not be fully, but ideally we can say all the real world characteristics of your real system or machine can be modeled using the model. So this is we cannot say, for example, we don't know what is happening in the space. So while designing a system, we need to model the space atmosphere within the Earth. So we need some kind of models for modeling that. For we, if you have heard about the in mechanical engineering, there is air tunnel. Air tunnel. That means the spacecraft or the flights modeling while it is on the flight, while it is traveling through the flight, can be modeled using the labs. Right? What they use, so instead of directly taking a flight into the air, what they do, they keep the flight in the lab and they pass the air in same speed which is in real case situations. So it is air tunnel, wind tunnel model, air tunnel model. This is some another thing, and that is before doing this we can do the simulation also. CFD, it's called CFD, computational fluid dynamics. So this is similar to in MATLAB also. This is things the, so CFD simulators are used to model the aeronautical things. So ultimately we are trying to model some real world thing. So in this example, ANN we can use to model some space, you can say character recognition, or say we can try to model a forecasting system so that we can predict whether tomorrow there will be rain or not, weather forecasting, temperature forecasting. People are using for a lot of things. If your data, you can use this to model a lot of things. Okay, so I think next things I will also share some code and small case study, a small example, so that we can get a feel how this is working, how NN is working in real life. So I think that is sufficient for today. If any doubts, I can take. Else, we'll stop. Any doubts?